Hello, I'm Mike McCulloch. Today I'd like to talk to you about globular clusters and a particular paper back in 2007 that was the one that convinced me that dark matter does not exist. So, as you probably all know, galaxies rotate far too fast to be held in gravitationally by the amount of matter we can see in them if physics is as it has always been assumed, well, the past few decades anyway. So astronomers add dark matter to galaxies to try and hold them in with extra gravitational force, but I find dark matter an extremely unpleasant and unscientific theory because it's added arbitrarily to galaxies to hold them in, which is very unscientific. It's never been spotted in 40 years. They haven't found it in their labs. And there are various other observations as well which show that it simply can't be true. For example, Lely et al. Showed that the rotation curve follows a light curve, which implies there's nothing dark affecting the dynamics. But one great falsification of dark matter was published in 2007, and it kind of slipped through the cracks, but I picked up on it. And this is a paper by Scarpa et al. shown here. And what they did was they said that, okay, so galaxy dynamics start to deviate from Newtonian physics at the edge where the acceleration is small, where the acceleration of stars happens to be very small. So they said, would there be any other places that we could look where the acceleration might be small, but dark matter could not be? This would enable us to identify the problem as being a small acceleration rather than dark matter. And this would imply a change to the laws of physics rather than dark matter. So they hit upon globular clusters, which are tight groups of stars within the galaxy itself, which have a low internal acceleration. So they're a little like little small galaxies, mini galaxies within the galaxy. And so they decided to have a look at that. And they plotted the rotational speed against the radius of the globular cluster. So the rotation speed, these diagrams that they plotted are shown here. So the speed up the y-axis is shown with as kilometers per second. So the x-axis shows the distance from the center of the globular cluster in parsecs. And what you can see in this plot is that, well, what should happen with any system is that as you go out from the center, the gravitational force reduces, and so the orbital speed you need to produce a centrifugal force to balance it should also decrease. So you should have what's called a Keplerian fall-off in the velocity. So it should simply decline towards zero. But in all these globular clusters, just as in galaxies, the velocity stays high, it plateaus at a particular velocity and stays flat. And Scarpa et al. Showed that in these clusters, this kink, if you like, this change from Newtonian fall-off to a plateau occurred at exactly the same acceleration that it occurs in the larger galaxies. But dark matter cannot be put into these globular clusters because when they add it to galaxies, they have to give it extra physics that makes it spread out and stay at the edge, because the center of galaxies are perfectly fine. So they can't force it to stay at the edge with new physics and then suddenly say that it congregates in globular clusters. So here they can't use the excuse of dark matter, and so there must be something else at play. And this implies also that this applies to galaxies as well, because galaxies are behaving identically. And so it implies that you need the same solution for both. And it looks like, because it occurs whenever the acceleration is below a particular value, it looks like a change to the laws of physics. And indeed, that this is exactly what quantized inertia predicts. And there's an older theory, empirical MOND, called modified Newtonian dynamics, which also explains it. But for MOND, there's no physical mechanism involved. And also with MOND, they have to put in an adjustable parameter. So it's not much better than dark matter, actually. You have to put in a number by hand to make it work. But quantized inertia predicts this number, and it predicts exactly where in the galaxies this change, this kink, should occur. So this paper really impressed me at the time and set me on track for trying to apply quantized inertia to galaxies. And it took about 5 years, but eventually I worked out how to model galaxies with it. And yeah, so I hope you've enjoyed this short. Now I've said all these extremely controversial things, I'm going to have to Scarpa myself. And I look forward to seeing you next time. Goodbye.